Hey guys, so in this video I wanted to introduce two ideas of two types of matrices. One being a unitary matrix, which encompasses unitary operations as well, and also Pauli matrices. So for the first one, unitary matrices. So these are definitionally are matrices that are any matrix U that satisfies this. So what this equation means is the conjugate transpose. This means conjugate transpose, as we talked about 2 videos ago, times the original matrix U is equal to the identity matrix. So identity matrix. So this is just definitionally what a unitary matrix is. Now, the key condition that is applicable to the kind of quantum mechanics with qubits that we've been talking about before is that and by the way, they're always square matrices. So square / n by n matrices. These matrices always work with this operation, always operate under this condition. So let's say we have some quantum state vector V. The norm, or the length of the vector V, is always going to be the same when multiplied by a unitary matrix when it's inside the norm. So the norm of U times V is the same as the norm of V. So unitary matrices preserve norms. That's one of the key ideas of what unitary matrices do. So if you operate it on a quantum state vector, it doesn't change its norm. So it doesn't change its condition of being a quantum state vector. It is still a quantum state vector. And the other idea I wanted to introduce in this video were Pauli matrices. These are 3 matrices, sigma x, sigma y, and sigma z, that are very special because they operate. They have certain properties. So they're unitary matrices. They are what's called Hermitian, which means that the conjugate transpose of these matrices, let's say X, the conjugate transpose is equal to the matrix X. So all 3 of these matrices follow that property. And a key idea is that they also preserve norms. So sigma X is equal to 0, 1, 1, 0. It's just the n by n 2 by 2 identity matrix. Sigma Y is 0, negative I, positive I, 0. And then sigma Z is 1, 0, 0, negative 1. And another thing you might notice about these matrices is they're called traceless. So if you add the diagonals together, the main diagonal for each of the matrices, it's 0, meaning it has no trace. So yeah, that's what a Pauli matrix is, and it's unitary if you want to kind of do this operation yourself, meaning if multiplied by a quantum state vector, it keeps it a quantum state vector. It preserves its norm. So yeah, thanks guys, see ya.